So, welcome back after these interruptions due to COVID. So today I would like to talk about the strong Markov property. So I'm assuming that we have a space, and in this space, a Markov process. So xt, it's a continuous time. Markov chain. And so I will assume that we have a filtration. So ft will be a sequence of Sigma algebras. So for each t, ft, it's a Sigma algebra. So this is what's defining a filtration, right? So it's a sequence of Sigma algebras, and they are increasing. So fs, it's contained in ft if s, it's less or equal than t. And I am assuming that xt, it's ft measurable. So xt for all t is ft measurable. This is what I mean by that. Okay. So this is the context, and I'm assuming that xt, it's a continuous time Markov chain with respect to this filtration. Okay. So an example for this filtration, we have seen it already. It's ft given by, it's the smallest Sigma algebra generated by xs for s less or equal than t. But maybe you have a Markov chain which is Markov with respect to another filtration. Okay. What I mean by xt to be a Markov chain with respect to this filtration, what I mean is that the conditional expectation of the function of xt plus s given ft, that this is equal to the expectation starting from xt of fxs. So I'm assuming that it's a Markov chain with respect to this filtration. So I'm assuming that this identity holds for all function f times s and t. Okay, so this is my assumption. And now I will define stopping times and the strong Markov property of continuous time Markov chain, but based on this setup. So this is the general setup. And my first important definition, it's stopping times. So we have seen this definition in discrete time, so I'll extend it to continuous time. And in continuous time, there are some subtotal t, which here are very simple because we are working in a discrete space. So I'll say that function t from omega to r plus union plus infinity, it's a stopping time if for all t larger or equal than 0, t less or equal than t belongs to ft. Mind that here I'm taking less or equal. Okay? If you define it t less than t, you have to make some modifications in what I'll say. So my first claim, okay, maybe we start with some examples. And I will present the same examples that we have seen in discrete time. So the heating time, so if I call H A, it's a subset of E. The first time you hit A, so this is the infimum over all t larger or equal than 0 such that xt belongs to A, then what I claim that this is a stopping time. So let's check. I have to show that HA smaller or equal than T belongs to FT. So what means that HA is equal to T? It's less or equal than T. Here is T. Well, I will divide this event in two events. And I will use the fact that our process xt is right continuous. So I'll say that, well, we have HA less than T and HA equal to T. So let's look at the first one. What does it mean that HA is less than T? It means that, well, at some point between 0 and T, I hit A. And how can I express this? Well, I will use the fact that the process is right continuous, and since the space is discrete, it is constant, locally constant. So it means that if you hit for the first time A at this time S, you will remain at S for at least a short period. It's really positive period because the process is right continuous and the space is discrete, which means that it's constant in a small interval, which means that you can find a rational number larger than S for which this process it belongs to A, which means what I'm saying is that if A is smaller than T, this means that I can find S smaller than T, S rational, such that XS belongs to A. Okay? So if you hit A before time T, you can find this rational time smaller than T for which, so if here it's HA, you can find S rational smaller than T such that XS belongs to A. And if this happens, of course, HA is also smaller than T, so these two sets are equal. We have assumed that XT is FT measurable, which means that this set belongs to Fs. And since this is a filtration, and S is smaller than T, so this set belongs to Ft. Right? While if HA is equal to T, what does it mean? It means that, well, at time T, the process belongs to A, so Xt belongs to A, and that it never hit A before time T. And I claim that this is exactly equal to the intersection for S smaller than T, S rational, that XS does not belong to A. Okay? Because, well, if it doesn't belong to A for all S, rational, it means, since it's right continuous, that it's different from A for all S. And again, we admitted that Xt is Ft measurable, so this set belongs to Ft. These sets belongs to Fs, which are included in Ft, and therefore we proved that indeed the heating time of A, it's a stopping time. Okay? So I leave it to you as an exercise to show that the return time, it's also a stopping time. So let me define the return time. So the return time, it's the first time after the first jump at which you hit the set A. So this is the infimum for all t larger than tau 1, and I will define tau 1 in a second. such that xt belongs to A. So tau 1 is the first time, the first jump time. So this is the infimum over all t larger than 0 for which xt is different from x0. So tau 1, it's the time at which you jump. And the return time is the first time after the first jump at which you hit A. So while HA can be equal to 0, H plus A, the return time, it's always larger than tau. Larger than tau 1, so larger than the first jump, so strictly positive. Because we've seen that the first jump, it's an exponential random variable. So that's fine. So let me show that tau 1 is hitting time, and let me define actually the jump times. So tau 1 I just defined, it's the time of the first jump, and let me define by induction tau k for k larger than 1 to be the jump times of this continuous time Markov chain. So tau k plus 1 will be the infimum for t larger or equal than tau k, such that xt is different from x tau k. So it's sequence of times at which the chain jumps. And what I claim is that these are stopping times. And let me prove that tau 1 is a stopping time. And I will leave to you to show that actually all jump times are stopping times. So again, we have to check that tau 1 less or equal than t, it's ft measurable. So what it means that tau 1 it's less or equal than t? Well, it means that you jumped. So this means that either, so what I claim is that tau 1 is less or equal than k, that either xt is different from x0, or there exists an s smaller than t s rational such that xs is different from x0. So either you jumped before time t, so you jumped here, which means that you started from some point, you remained there and it jumped. Since you jumped at a time tau smaller than t, this means that I can find a point s rational smaller than t for which xs at this point is different from x0, or you jumped exactly at time t, which means that xt is different from 0. Okay. Fine, and all these sets are ft measurable. So these are examples of stopping times. Well, so now I claim that if t is a stopping time, then the set t less than t belongs to ft. Okay, by definition, the set t less or equal than t belongs to ft. Let's show that t strictly smaller than t also belongs to ft, and this is very easy because I can rewrite this as a union for n larger or equal than 1, that t it's less or equal than t minus 1 over n. Right, so this union is equal to that set. Each of these sets belongs to ft minus 1n, which is included in ft. Okay, but the other way around wouldn't hold. So if I had defined my stopping time by requiring that the strict inequality belongs to ft, I couldn't prove that the unstrict inequality was in ft. Okay? Okay, so these are simple observations. Now, a second definition, which we already have seen in the discrete time setting, is the sigma algebra ft. So if I have a stopping time t, I will define ft as the set of all elements A in F such that A intersection t less or equal than t belongs to ft. And this for all t. And again, the interpretation is that ft is all the information available to you at time t. Now we have a stopping time. So let's say the first time you hit a set. This time it's random. But you can now, you want to give a sense to all information available to you up to that time. And this is what ft means. Okay? So ft, this sigma algebra, it's all the information you have at your disposal at this stopping time t. So again, simple facts. I claim first that if S and T are stopping times, so these are stopping times, and assume that S is less or equal than T, then what I claim is that the sigma algebra Fs it's contained in Ft. Okay, so let's take an element A in Fs. I want to prove that it belongs to a Ft. So to show that it belongs to Ft, I have to consider the set A intersection T less or equal than T and show that it belongs to Ft. But since S is smaller than T, if T is less or equal than T, then S it's also less or equal than T. So I can include in this these two sets coincide, right? Because T less or equal than T, it's included in S less or equal than T. So the intersection of these two sets, it's equal to that one. And now, since A belongs to Fs, this set here belongs to Ft. T, it's a stopping time, so this set belongs to Ft, and therefore the intersection belongs to Ft. So that's easy. So that's the first claim. Then let's prove that if I take S less or equal than T, then this set belongs to Ft, and also S less than T belongs to Ft. So I take two stopping times, and I want to show that these two sets belong to Ft. So my second claim, say, just to make it clear, I have two stopping times. S and T are stopping times. Okay, and I claim that, so I'm not assuming anymore that S is less equal than T. I'm just taking two stopping times, and what I want to prove is that these two sets belongs to Ft. Okay, so let's prove the first one. So I want to show that S less than T belongs to Ft. So I take intersection T less or equal than T, and I have to prove that this set belongs to Ft. So let me write this again. Let me divide it as S less than T and T it's equal to T, union S less than T and T it's smaller than T. And let's consider separately these two sets. The first one, if T is equal to T, I can replace capital T by T here. T equal to T, I didn't say I should have, belongs to Ft. Okay, so T equal to T belongs to Ft because I can write this as T less or equal than T minus T less than T. And both sets we have seen are in Ft. So T equal to T belongs to Ft. So this one belongs to Ft. And if capital T is equal to small t, I can replace this capital T by small t, and I get S smaller than T, which is also in Ft. So the first line belongs to Ft. Now let's see for the second line. So here's T. I know that T is smaller than T, so it's somewhere here, and that S is smaller than capital T, so it should be somewhere here. Well, this means that I can find a rational number between capital S and capital T, smaller than S. So what I claim is that this second set, it's equal to the union of R rational, R smaller than T, larger than 0, such that S is smaller than R and R is smaller than capital T. Okay? Because, well, if S is smaller than T and T is smaller than, I can find such a number. And if it's true that there exists an R for which S is smaller than R and R is smaller than T, then it's clear that I need T less than T here also. Okay, to guarantee the second condition. Fine. But now, well, this is an element of Ft. This is the complement of T less or equal than R. So it's in Fr. And this one we have seen it's in Fr because S and T are stopping times. So from that we get that indeed this set belongs to Ft, which proves that S smaller than T belongs to Ft. Okay, and so now let's prove that S less or equal than T belongs to Ft. For that, it's enough to show that the complement of this set belongs to Ft. So what I will prove is that T smaller than S belongs to Ft. in order to prove that, we have to show that t less than s, intersection t less or equal than t, that this belongs to ft. And here again, I will divide this set in two pieces, t less than s and t equal to t, union t less than s and t less than t. So again, for the first one, it's easy because, well, t equal to t, we have seen it's in ft. Then I can replace capital T by small t, and s larger than t, it's also in ft. So for the first line, there is nothing we need to say. So let's consider the second line. So t is smaller than t, so it's somewhere here. And s, it's larger than t, so it can be here, but we can always find a rational which is smaller than t, because t is smaller than t, and which separates t from s. So what I claim is that the second one, I can find an r smaller than t, r rational, such that t is smaller than r and r is smaller than s. Okay, and here I don't need to include t smaller than t because r is smaller than t, so it's already included here. And these sets are equal, and again, this set belongs to ft. Now you can take the complements to see that, well, all these sets belongs to fs. Okay? So this is what I wanted to say about some properties of stopping times. Yes, there is one which is missing. I want to say that xt belongs to ft. This is another important property. So let's say a lemma xt, it's ft measurable. So proof. So we have to show that the set xt belongs to A. To show that this random variable is ft measurable, I have to take the inverse image of any set, but here we are in a discrete finite set, so we have to show that for any subset A of E, xt belongs to A, it's in ft. And to show that this set belongs to ft, we have to prove that if xt is in A and t is less or equal than t, then this set belongs to ft. So this is what we need to prove. Fine? So again, I will divide this set in two. The first one, it's xt in A and t equal to t. And this, we have seen, this set belongs to ft. And if t is equal to t, I can replace t by t. And xt, it's ft measurable by assumption, by hypothesis. So this one is fine. And what we need to consider is the second one. So the second one, it's xt in A and t less than t. And again, I will use the fact that the process is right continuous. So the idea is as follows. Here is t. And what I'm saying is that what I'm claiming is that if t is smaller than t, then there exists an integer n. So what I intend to do is to divide this set in intervals of size 1 over 2n. Okay? Then, since t is smaller than t, for n sufficiently large, this difference will be larger than 1 over 2n. So this means that there exists an n such.
What if you want it to be smaller?
Larger, you'll see. So since t is smaller than t, I can find n for which this difference is larger than 1 over 2n. And why? For all n sufficiently large. So there exists an n which such that for all m larger than n, there exists a k. So I will divide this interval in now intervals of size 1 over 2m. And what I claim is that t will belong to the interval k over 2m k plus 1 over 2m. So this is always true, but what I want to say is that I can stop this union. So here is t. What is, I want to approximate t, so in this scale 2m, this point will be the point t times 2m divided by 2m. And the next point will be here t 2m plus 1 divided by 2m. Right? And so I will stop in here I have the same thing for t, right? So this point here, okay. So t, sorry, it's larger than this point here will be t 2m divided by 2m, and this point will be t 2m plus 1 divided by 2m, right? So what I want is to stop at this interval. So my union here will be from 0 up to t 2m minus 1. Okay? So I'm stopping here. This is my last interval in this union. Okay? And what I claim is that since the difference between capital T and T is larger than 1 over 2n, m is larger than m, so it's also larger than 1 over 2m, which means that T indeed belongs to this interval. So I can indeed stop here. Do you agree? Or isn't it clear? Should I repeat what I'm doing? So what I'm saying is that I have my interval here up to t. And t is somewhere here. And this difference, it's larger than 1 over 2n. Okay? Now I fix m larger than n. And I cut my interval in intervals of size 1 over 2m. Okay? So, and I have here 1 and the other one. Okay? So which one is this one? This is 2m multiplying t. I take the integer part of that, and I divide that by 2m. Okay? So this is smaller than t by definition of the integer part. And so the next one is this one. Okay? Now I'm taking all the intervals between k over 2m and k plus 1 over 2n up to t 2m minus 1. So here is 2m t minus 1 divided by 2m. So I'm stopping at k equal to this number, 2mt minus 1. So the last interval I'm taking is this one. Okay? So what I claim is that t indeed belongs to one of these intervals. The only piece which in the interval 0t which I'm taking out, it's this piece. But the size of this piece, it's smaller than the size of this interval, which is 1 over 2m. So this distance, it's less than 1 over 2m. And I'm assuming that the distance between t and t is larger than 1 over 2n, and therefore larger than 1 over 2m. And therefore, indeed, t has to be on the left of this point. Do you agree? Okay. So this means that indeed there exists an n for which, for all m larger than n, then I can stop at this integer. And this is that t is smaller than t. Okay, so what I proved is that these two events are equal. And now, if I take the intersection xt belongs to A, this means that this set, so I can erase, so that the set xt belongs to A, intersection t smaller than t is equal to this union xt belongs to A. All right? But since the trajectory is right continuous, it means it's constant. So at t, if I fix an omega, the trajectory will be constant on an interval of some size epsilon after t. So if I take m sufficiently large for this interval to be larger than 1 over 2m, remember that t here belongs to, it's in this interval. If this size is larger than 1 over 2m, this means that x at this point it's equal or belongs to A. All right? I know that t belongs to this interval, k to m, k plus 1 to m. So t is somewhere here. And now I'm taking m. So I know that t is constant in an interval of size epsilon. So if I take m such that 1 over 2m, 1 divided by 2 to the power m, it's smaller than epsilon, then the value at this point, it's also equal, well, it's equal to this value, and therefore these two events are the same. Okay, so what I'm saying is that, well, this set, it's equal to the same set in which I replace xt belongs to A by x k plus 1 divided by 2m belongs to A. And now, all k's here which are appearing are less than t to m, the integer value of t to the power 2m. So when I'm taking here plus 1, this becomes t to m, the integer value of t to m divided by 2m, and this is smaller than t. So all these events belong to ft, right? Because the last one, k plus 1, it's k, it's equal to that. K plus 1 will be equal to this, and this is divided by 2m, it's smaller than t. And therefore, all these sets belongs to ft. And this proves that xt is ft measurable. Okay. So questions?
In the previous proof that the events that strictly smaller, I mean the event that S is strictly smaller than T, could you use the time T plus 1 over n? Because it's to make the countable intersection of the events, maybe you could use that to prove.
I'm not sure if I understood, but we can discuss that at the end of the class. You want to take t minus 1 over n or t plus 1?
And intersect over the natural number.
I think that is fairly to surprise with the continuity of the Sigma Algebra.
I think if we would use minus, I think that we would have tried, but you know.
Okay, we discussed that at the end of the lecture. Okay, fine. So this proves that xt belongs to ft. Now, I want to prove the strong Markov property. So theorem, and so keep in mind that I'm not using the construction of the Markov chain we did. I'm just using the assumption I wrote at the beginning of this class. Right? We have a Markov chain, and it's ft measurable. It's Markov chain with respect to ft. So the theorem is that if t is a stopping time, then it holds that the conditional expectation of fxt plus s. So s, it's a real number, given the sigma algebra ft, that this is equal to the expectation starting from xt of fxs. So this means that for all f, well, if you want to start at some point y for all y, and for all s positive, then this holds. Okay? So I'm here replacing a time which is deterministic by a stopping time. And what I'm saying is that, well, the same identity holds for stopping times. Yeah. And this is on the set where t, you're absolutely right, on the set where t is less than infinity, otherwise xt is not defined. Okay, so this is what I want to prove. The proof goes in two steps. I'll first assume that t is discrete. So I'll assume that there exists a set tj, so with no accumulation points. So let's say it's an increasing set. And for which the probability that t is less than infinity, it's equal to the sum of the probability that t is equal to tj. So I'm assuming that t takes only a countable increasing number of possible values. And what I claim is that, well, if this is true, then I can prove this result. So, in order to prove this, what I have to show is that the expectation on set A intersection t less than infinity of fxt plus s, that this is equal to the expectation of qa intersection t less than infinity, the expectation xt fxs. Right, we know already that xt is ft measurable. I just proved that. So this function is ft measurable. Therefore, to prove that this conditional expectation is given by that, it's enough to show that this holds for all a in ft. And I will simplify this. Since E it's a finite set or countable set, I will add here that xt it's equal to x, and here that xt is equal to x. Because if I prove that for all x, I can just sum over x on both sides, and I will have the previous identity. So it's enough to prove that. And if xt is equal to x, I can here replace xt by x, and what I have to show is that this is equal to expectation starting from x of fxs, expectation or probability of A intersection t less than infinity intersection xt equal to x. So this is what I want to prove. I want to prove that these two expressions are equal. And in my case, in which t takes only the values tj, it's enough to prove this identity in the case in which t is equal to tj. So it's enough to prove so under this assumption that t takes only these values, I can replace here the fact that t is less than infinity by t equal to tj. So it's enough to prove that for all j, the expectation of chi A intersection t equal to tj intersection xt equal x of f xt plus s, that this is equal to the expectation x fx probability that A intersection t equal to tj intersection xt equal to x. So this is what I will prove. And this proof is very easy because, well, it's a consequence of the Markov property, because if t is equal to tj, I can replace t here by tj. Right? T is equal to tj, so I can replace. And I can replace it here as well. Now, I know that A belongs to ft. This means that A intersection t equal to tj belongs to ftj, because t equal to tj can be written as t less or equal than tj minus t less than tj. Okay, so this event A intersection t equal to tj, I can rewrite that as A intersection t less or equal than tj minus A intersection t less or equal than tj minus 1. Okay? This set belongs to ftj, this to ftj minus 1, and therefore this set belongs to ftj. Okay, so this set belongs to ftj. And therefore, I can just take the conditional expectation with respect to ftj in this on the left-hand side. So if I take the conditional if I write the expectation as the expectation of the conditional expectation given ftj, well, this set is ftj measurable. We have seen that xtj is ftj measurable, so they get out. And I get the conditional expectation of f x tj plus s given ftj. Right? So I just replaced t by tj, and now I took the conditional expectation with respect to ftj. By doing that, I removed from the conditional expectation all variables which are ftj measurable. What remains is this conditional expectation, but now we have here a conditional expectation with respect to a deterministic time. So by assumption, this process, it's a Markov chain with respect to this filtration, and therefore this is equal to the conditional expectation starting from xtj of fx. And this is exactly what I wanted, because now I can replace xtj by x. So this becomes a number, gets out from the expectation, and what I get, it's exactly the expectation starting from x of f of xs, and then the probability of A intersection t equal to tj, xtj equal to x. And this is exactly what's written here, provided I replace back tj by capital T. Okay? So when the stopping time, capital T, takes only a countable number of values which are increasing, strictly increasing, and converging to plus infinity, or with no, we could take it finite, so we don't need tj to be infinity, we just need this family not to have accumulation points. Right? So it could be a finite number of values. So we have here a proof in this case, which is essentially reduced to the usual Markov property. So now let's extend this proof to the general case. So questions about that? Okay. So what we will do is we will reduce the general case to this situation. So we have a stopping time t, and now I want to define a sequence of stopping time satisfying this property and converging, decreasing to t. So the idea is to define now a sequence of stopping times, tn, which have this property and are decreasing to t. So tn will be equal to 0 if t is equal to 0. So if t is equal to 0, we just set tn to be 0. Otherwise, well, if tn belongs to the interval k2n, k plus 1 to n, so I'm fixing n. If t is not 0, it belongs to such an interval. So if it belongs to this interval, I will set tn to be k plus 1 divided by 2n. Okay. So what I claim is that tn, it's a stopping time, that tn are increasing, or decreasing, sorry, and they are decreasing to t. Okay, so my claim is that tn is a stopping time, that tn decrease and decrease to t. And clearly, Tn satisfy this assumption. Okay? So Tn assumes only values k divided by 2n. So the strong Markov property holds for Tn. So let's prove that Tn is a stopping time and that it's decreasing. So to prove that Tn is a stopping time, we have to ask yourself, well, Tn less or equal than t has to belong to Ft. But Tn, if you have t here, okay, if, let's say, maybe, let me cut it in two. Let's assume that t is different from k to n for all k. And so when it's Tn less or equal than t, we have here k to n, k plus 1 over 2n, where k0 maybe, and k0, it's equal to 2n t. How? Okay, I don't know how to do it in a simpler way. I'll just divide that in according to if t is equal to 0. If t is equal to 0, then Tn is less or equal than t. This is because Tn is equal to 0, and this set it's Ft measurable. Okay? This set it's if t is equal to 0, Tn is equal to 0, so this is always happens, so this set coincides with t equal to 0, which is F0 measurable, which is Ft measurable. Okay? So now, what happens if t is larger than 0? Then let me take union for g larger or equal to 0, and here I'll take so in this set, I want Tn less or equal than t. Okay. So here I'm taking intersection t larger than 0. And so these sets are equal. Now, if t it's between g over 2n and j plus 1 to n, Tn it's equal to j plus 1 over 2n. Right? In this interval, j takes the value of the right-hand side. So this means that j plus 1 to n, it's less or equal than t. So this is saying that, well, I'm actually doing this union for j between 0 and I want j plus 1 divided by 2n less or equal than t. This union, it's performed only over all j's for which j plus 1 divided by 2n, it's less or equal than t. Okay? And this set here belongs to f j plus 1 divided by 2n. And since I'm doing this union over these j's, this means that this j plus 1 divided by 2n is smaller than t, and therefore this set it's contained in Ft. And therefore this set belongs to ft. Okay? So this shows that indeed Tn it's a stopping time for all n. Now we want to prove that this sequence it's decreasing. Well, it's clear that T it's bounded by Tn. Okay, because well in this interval we defined it to be k plus 1. So we know that Tn it's larger than T. Of course, the difference between Tn and T, it's bounded by 1 over 2n. So Tn, it's indeed converging to T. Let me just prove that this sequence is decreasing. So Tn plus 1, it's smaller or equal than Tn. Okay? So this sequence, it's bounded below by T, it's decreasing and converging. So it's converging in a monotone way to T. Questions about the previous proof?
But in this way, you want that the convergence to be uniform or?
No, just pointwise. For all omega Tn, it's converging to T.
Yeah.
But it's decreasing.
But it's not uniform for in this case.
Well, it's uniform in this sense because this difference is bounded uniformly by 1 over 2n. So the supremum, it's converging. But I won't use that. You look not convinced. No, it's okay? Okay. So let's go back here. What I claim is that this sequence, it's monotone, so it's decreasing. Why is that so? So here is the interval, say, k to n, k plus 1 to n. Okay, and t, let's say that t belongs to this interval, somewhere to this interval. Okay, so for Tn, if k belongs to this interval, this is the value of Tn. Right? Now let's look at what happens at n plus 1. So this point corresponds to the point 2k 2n plus 1, and this point 2k plus 2 2n plus 1, and there is the middle point here, which is 2k plus 1 divided by 2n plus 1. Okay? So if t belongs to this interval, if t is somewhere in this interval, this is the value of Tn plus 1. And so you get that Tn plus 1 is indeed smaller than Tn. While if the point t belongs to the second interval, then the value of Tn plus 1 is equal to the value of Tn. Therefore, in both cases, Tn plus 1 is less or equal than Tn. So Tn, it's indeed decreasing. It's larger than T, we have seen. And the difference between them, it's 1 over 2n. This means that Tn, it's indeed decreasing to T. So we constructed a sequence of stopping times which are monotonely decreasing to the stopping time T. And for these stopping times, we know that this holds. So we know that this identity holds if I replace T by Tn. Okay. Mind that the set T less than infinity, it's equal to the set Tn less than infinity. And in this set, I have that the expectation of y of f x tn plus s qa So I'm just rewriting the identity for the stopping time Tn. So we know that this identity holds for all A in Ftn. Okay? This is what we proved. Right? And for all S positive. Now let me take A in Ft. So I take a set A prime, let's say, in Ft, or B, just not to mix with this one. So let me take a set B in Ft. T, it's smaller than Tn, so we have seen that Ft, it's contained in Ftn. So since B, it's in Ft, it's also in Ftn. So I can take A equal to B, this identity, it holds for this set. Now, as we have seen, Tn it's finite if and only if T it's finite. So I can replace Tn finite by T finite. And now I finally can use the fact that Tn it's decreasing to T. Since the process is right continuous, this means that xtn, it's converging to xt. This is why it's important to have a decreasing sequence, because the process is right continuous, it's not left continuous. So since tn is decreasing by 2t, xtn, it's converging to xt, almost surely, for almost omega. And therefore, we can just apply the bounded convergence theorem. Okay? F, it's a finite function, so if I let n to infinity, since xtn plus s, it's converging to xt plus s, this will converge to the same expression replacing tn by t, and the same thing here. And this extends the strong Markov property. So you see, the proof is very simple. So it's not difficult to extend the Markov property to the strong Markov property, but the strong Markov property, it's, we'll see, extremely useful. Okay, it means that at any stopping time, you can think that, well, the process is starting afresh, that you can forget everything which happened up to that time and just start your process at this position. Okay? So questions? So these are, okay, so I'll still prove some properties, general properties of Markov process, but now we'll stop our study on Markov process and start discussing interacting particle systems and hydrodynamical limit. Okay. And for these first lectures, I strongly recommend you to read the book by Landau and Lifshitz, which is called Statistical Physics. And in some sense, what we are trying to provide here, it's a model, which is a stochastic model of course, Landau and Lifshitz consider only, well, the case of Newtonian dynamics, so you have essentially a dynamical system, so molecules evolving. But here, what we will do is that instead of considering these deterministic evolutions, we'll consider stochastic one. But if you read Landau and Lifshitz, you'll see that what we're doing is exactly what they have in mind in a slightly different context, because we are here admitting that the evolution is stochastic instead of deterministic. And the model which I want to introduce, it's called the simple exclusion process, which I already started to present in a previous lecture. So the idea is that we have, let's say, just to fix ideas, a one-dimensional torus, and I will cut this one-dimensional torus in intervals or cells of size 1 over n. So I fix n. N will converge to plus infinity, so n it's very, very large. And I cut all these torus in these small cells. So I will represent that by a line which I identify both n's. So we have here, say, 0, here 1 over n, 2 over n, and so on, up to n minus 1 over n. And what I think is that this represents what we want to represent, our particle moving in this space. And let's say that we took cells very, very small in such a way that no two particles can occupy the same cell at the same time. So what we have is, let me call lambda n these discrete torus. So can also represent it by Tn, which is a discrete torus, which will be 0, 1 over n, up to n minus 1 over n. Just keeping in mind that we are identifying the point 1 with the point 0. So this is a discrete torus. If you prefer, you can think it of a d-dimensional torus. Everything I will say apply to the d-dimensional case. And then we have particles moving in this space. So here are the particles. And as I said, I will assume that there is at most one particle at each point. So my state space, which I say will represent by omega n, will be 0, 1 to the power lambda n. And recall my notation, I will represent the configurations by Greek letters eta xi. So eta will be a sequence of eta 0 and eta e, eta 2e up to eta n minus 1 e, where from now on e will be 1 over n. So eta ke will be either 0, 1, 1 if the point ke is occupied, 0 if it's empty. So this is my state space. Now let me remind you of the dynamics I introduced. So these particles are moving. And there are several ways in which you have to think of this process. One way at which you can think is that each particle, it's moving. So it waits, it tries to jump to the right at rate 1, and to the left at rate 1, which means that these particles, if the rate is 1 and 1, this means that there is a rate 2 of moving, so that it waits an exponential time of rate 2. Okay. And at the end of this time, so when this clock, exponential clock rings, it tries to jump to the right or to the left with probability 1/2. As I said, well, in these dynamics, you do not allow more than one particle per site, which means that if the particle decides to jump over a site which is already occupied by a particle, this jump is forbidden. So particle does not jump. But if it chooses to jump to a site which is not occupied, which is empty, the particles just jump. So you can think in this process in this way. Each particle waits its own exponential clock, which is independent from the others. This exponential clock has rate 2, and at the end of this clock, it decides to jump to the left or to the right with probability 1/2. So this is one interpretation. So each particle has a clock. These clocks are random, they are exponential, they are independent, and each time the clock rings, you try to jump to the right or to the left. Okay, so this is one. What I will propose, it's two descriptions, one which is analytical, because I already introduced Markov process, and the other one which is graphical. So here is the analytical description of these dynamics I want to introduce. Well, I told you that if I want to define a continuous time Markov chain on this finite state space, what I need to tell you are what are lambda and p. Okay? So in order to define lambda, so I tell you what is lambda and what is p in this process. So remember, lambda are the parameters of the exponential random variables, and p are the jump matrix. Okay? So let me fix a configuration eta, and let me introduce the neighbors of eta. So I will represent by n of eta the set of neighbors of eta. So these are all configurations which can be obtained from eta by moving a particle to the left or to the right. So the neighbor of eta are all configuration psi such that there exists an x in lambda n. So remember, lambda n is our set, such that psi is equal to sigma x plus e of eta. And what is this configuration sigma x plus e of eta? Well, it's the configuration which you obtain from eta by exchanging x and x plus e. So this is a new configuration which at y, it's equal to eta of y, if y is different from x to x plus e. Remember, e it's 1 over n. And if y is equal to x, this is eta x plus e. If y is equal to x plus e, this is eta x. So let's see here in our example, here is a configuration. Okay, so let's go back. We have here a configuration with 4 particles. So let's see who are the neighbors. Of this configuration. Well, one neighbor, so let's go x by x. Okay, so let's take all x in lambda n. So let's start with 0. And So the configuration sigma 0 e of eta will be the configuration in which we exchange. So here we get a first neighbor, which is this configuration, in which I exchange 0 and 1 over n. So if I now exchange 1 over n and 2 over n, I got a new neighbor, which is this configuration. Now if I exchange 2 over n and 3 over n, I got a new configuration in which this particle jumped to 3 over n. Now I have here, well, if I exchange now 3 over n and 4 over n, nothing happens because both sides are empty. So I don't get a new neighbor for this configuration. But if now I exchange particles between these two sides, I get a new configuration, which is this one, in which this particle moved to the left. If I exchange these two, nothing happens, because both sides are occupied. But if I exchange these two, I get a new configuration. And then I go up to the side when I exchange n minus 1 with n. But remember, n is 0, and here I get a new configuration in which this particle disappeared and went to the side n. So I get, so these are all neighbors of my configuration eta. And as you see, how many there are? Well, 1, 2, 3, 4, 5, 6. So there are 6 neighbors, which are all represented here. 1, 2, 3, 4, 5, 6. Okay, so these are the set of neighbors. Definition clear? So these are the sets of neighbors, and lambda of eta so lambda of eta is just the number of neighbors. Okay, so if I have a set, absolute value of the set means the number of elements of this set. Okay? So this is lambda. So if I have a configuration with only one particle, the set of neighbors are exactly equal to 2. This was my observation at the beginning, that you can think that if you have a particle, this particle tries to jump to the left or to the right after an exponential time of rate 2. Now, p eta of xi will be equal to either 1 over the number of neighbors if xi belongs to the set of neighbors and 0 otherwise. Okay? So what is the dynamics? You are at the configuration eta. You wait an exponential time of rate lambda of eta, which is number of neighbors. So if you have many neighbors, you jump quickly. If you don't have that many neighbors, you jump slowly. So the rate is equal to the number of neighbors. And once you decided to jump, you choose uniformly among your neighbors. So this is the dynamics. Okay? Fine. So now, to understand what's going on, let me give you a graphical construction. So here's my set. And I will add here a point just to say that this point is the same as this one, okay? Because we are working here on the torus. So what I will do is between two sides. So I have here edges, sides and edges. So in these edges, I will draw a sequence. So time is going downward. So this is time. And maybe blue, it's not very easy to see. So between two sides, I will draw exponential random variables of rate 1. So here it's a first T1, 1 will be an exponential random variable of parameter 1. So this is the size of this random variable. Then I have, say, here T1, 2. So 1, because I'm here taking between the site, let's say that this is site 1 over n, and this is site 2 over n. So to say that this is between 1 and 2, I'm putting this superscript 1. And so these are just IID, random variable. They are all exponential, rate 1. And I will do here the same thing. So let's say that here I have only one here. So this is tau 2, 1. And let's say that here I have a second one, tau 2, 2, and so on. And I do that for all edges, or for all interval between points. And I don't forget to add 1 here, which corresponds to the edge between n minus 1, n and 1 over n. Okay, so here, and let's say that instead of, well, I just draw crosses. Okay, they are not equal. Okay, so let me remove one edge and say that this is okay, so here it's 1, 2, 3, 4, 5, 6, 7, and this is 0. And this is, this is 1. Okay, so n equal to 7 in my example. So remember, here, this is an exponential random variable. It represents the value of an exponential random variable. And from this cross up to the next one, it's also an exponential random variables. All are independent. So this one is independent from that one. Everything here is independent and identically distributed, and they have all rate equal to 1. Okay, is that clear? Okay, so so let me erase the names of these random variables. To have a clean picture. So this is a typical realization of my process. So now what I will do is each time I see a cross, I will draw an arrow between the 2 points. So here there's a cross, so there is an exponential random variable. So I will draw an arrow between the points, the neighbor points. Okay, so same thing here, and same thing here. Here also, here also. Okay? So these are the arrows I just draw. Now I will start with the configuration, and I will describe how this configuration evolves in time. Remember, time is going downward. So maybe let's have something simple. So let's say that we are starting with two particles, one here, and say the other here. Okay, so this is my initial configuration. So this is my configuration at time t equal to 0. So at time t equal to 0, I start from a configuration, which, I'm sorry, these particles are over the sides. So with a particle at side 2 over n, and a particle at side 3 over n. So this is my initial configuration. Okay. Now, what I will do is I follow time until I find an arrow. So when I get an arrow, which is the first time in which these particles find an arrow, is at this time. At this time, I let the particle jump to, it just follow the arrow. So at this time, this is the configuration. Because this particle found an arrow, so it jumped to the right. Then at this, so this is, see, the first jump. Second jump will happen here. This particle jumps here. So the configuration at this time, tau 2, will be this configuration. And then they follow. So the next jump will happen at this time. So this time, it's a new jump in which this particle goes back to the side 2 over n. So this is the configuration at time tau 3. Then they go. Here, this particle jumps. And now here, well, they just exchange position, so nothing happened with this. And finally, at this time, this particle jumps here. So this is the position at this time. Okay? So this is how to construct this process. And now let me let me convince you that indeed what we observe is an exclusion process. So let me prove that indeed my construction gives me lambda of eta equal to the number of neighbors and p of eta equal to the uniform measure. So my claim first is that lambda of eta is equal to the number of neighbors of eta. So let's see in this example, when will this configuration jumps? Well, when they first meet an arrow, either between 3 and 4 or between 1 and 2. So this configuration will only change when I get an arrow between 3 and 4 and 1 and 2, right? If I get an arrow anywhere else, nothing will happen to the configuration. Okay? But when do I have an arrow between 3 and 4? Well, this time, it's an exponential time of rate 1. And this time, it's an exponential of independent from the first, which is also of rate 1. So the first jump will happen at the minimum between 2 exponential times of independent of rate 1. So they will jump at exactly exponential time of rate 2. Okay, because the minimum between these two, you just add up. And this is exactly the number of neighbors. And if you had more particles, you'll just get, well, where they can jump, which means the number of neighbors they have, and it will be a minimum between all these exponential times. So the jump time will be indeed an exponential whose rate is given by the number of neighbors. Okay, if I had here a particle, then I'm adding 2 new exponential random variables because I'm adding 2 new neighbors. And now, let me show that P is uniform. Well, in my example, we have two neighbors. When will the particle jump to this neighbor, in which this particle jumps to the right? Well, that will happen if this exponential clock, this exponential random variable, is smaller than that one. But since they have the same rate and they are independent, this probability is just 1 over the number of exponential clocks, random variables. So it's uniform. If you had an extra particle here, you could ask what is the probability that this one will jump to the right, so that this particle, this configuration will move to this neighbor in which this particle jump to the right. Then it's exactly the same thing. For that to happen, I need this random variable to be smaller than all the other ones. And this is exactly 1 over the number of variables. So 1 over the number of neighbors. So that gives me exactly that P is uniform. Okay? So this is a graphical construction of my process. I construct this process with IID exponential random variables of parameters 1. I just need, well, many of them. Okay? But if you take for each bond, for each edge, you take a family of exponential random variables, then you can construct your process. Okay? So this is one point. The second point is now you are at time t, and you ask yourself, well, what is the probability that this site is occupied at time t? This is not a site, sorry. This site. What is the probability that this site is occupied? Is this site occupied or not? Well, what you need to do in order to see if this site is occupied or not, is go backward in time by following the arrows. So this site, well, corresponds at time 0 to this site. Okay? So if I want to know if this site is occupied or not, I just go backward in time and I follow the arrows. So there is no error between this point and the other. So what will tell me if this site is occupied or not at time t is the fact that this site 2 over n is occupied or not at time 0. And what is the evolution? How this particle evolves? Well, it evolves, it waits for the first arrow to the right or to the left. This happens, these are exponential random variables. If you take the distribution, if you fix a time t and you look at the first arrow backward in time, it's also an exponential. That I didn't prove, but you can check. So this is also exponential random variables of rate 1. So what you wait, it's an exponential random variable of rate 2. And you jump to the right if the arrow to your right appeared before the arrow to your left, so probability 1/2. So what you're doing backward in time is that you are weighting exponential rates of exponential random variables of rate 2, and then jumping to the right or to the left with probability 1/2. So this is what we call the random walk. So what you're doing is you're following a random walk, and so the position at time t is given by a random walk, which evolves up to time t and reach a position at time 0. So backward in time, what you're observing is a random walk. Now, if you are interested in two particles, in two sites, what they will do is that they will act as random walk until the first time where they are neighbors. At this time, there is an interaction between them, because if they decide, they might decide to jump at the same time. Okay. So these random walks are not independent. they are not independent because sometimes they will jump together. And therefore, computations are more delicate for that. Okay. But these are just comments. My question to you is that, do you agree that this is a graphical construction? So that the construction I proposed gives exactly, yields exactly the Markov chain I described. That lambda is indeed given equal to the number of neighbors, and that the jump transition is uniform. It's okay? Okay. So remember, I have a generator, and I can write the generator of this process we have seen as L of eta. It's equal to the sum over all xi's in our configuration space of the rate at which you jump, but the rate at which you jump, so let me write R eta xi, will be equal to either, well, it's equal to lambda of eta p eta xi. Okay, so this is equal, lambda, it's the number of neighbors, so this is 1 if xi belongs to n of eta and 0 otherwise. So the jump rates, which are the multiplication of lambda with p, it's equal either 1 if xi belongs to eta and 0 otherwise. So in my definition, this is R eta xi, f xi minus f of eta. Okay, so this was our generator, as I wrote before. We had rates. But now I know exactly what are the rates. So this is actually a sum over all xi in the set of neighbors of eta of 1 times f xi minus f of eta. Okay? I just replace R eta xi by 1 if xi is a neighbor, 0 otherwise. So this is the formula I get for the generator. And I can further simplify that as saying that this is a sum over all x between 0 and n minus 1 of f sigma x, x plus 1, x plus e of eta minus f of eta. Okay? Because here, what I'm doing, I'm just exchanging what happens at x and x plus e. So what happens? If I take an edge which is occupied and empty, I exchange, and I get a neighbor. If I get an edge in which both are occupied, when I exchange, I get the same configuration. And by getting the same configuration, so this configuration will be equal to eta, so this is just 0. So this means that in this sum, if this side it's not a neighbor, then this difference is 0, while if it's a neighbor, I get exactly what's written here. So this is an alternative way, a simpler way to write this sum, because now, well, I don't need to refer to the set of neighbors. Okay? So I think I'll stop here. Yeah, it's time to stop. And in next lecture, we'll start to discuss the invariant measures. So you see that this process is not irreducible because the total number of particles is conserved. It's kept constant in time. So for each k, where k represents the total number of particles, I have a set from which I cannot jump from this set to a set k plus 1 and k minus 1 because the total number of particles is conserved. So I'll discuss a bit of that. Okay, so thanks, and see you on Tuesday then. Você quer discutir, então? Eu não entendi o que você